Hey guys, today we're going to look at hypothesis test, one sample means. I'm going to go through the nuts and bolts of a hypothesis test, and we're going to go through one complete example. Then I'll do a second video with two other examples if you need some additional help. So grab a pen and let's get going. Let's say a government agency has received numerous complaints that a particular restaurant has been selling underweight hamburgers. I mean, the travesty. This is a big deal. The restaurant advertises that its patties are a 1/4 pound or 4 ounces. I mean, we all know what's going to happen here. If the patties are really found to be underweight, somebody's going to sue. And if they're overweight, well, the restaurant's giving away free beef, and they're certainly not going to like that either. How can we tell, though, if these patties are really less than the 4 ounces they're advertised to be? You guessed it. Let's take a sample. Let's take a sample and find X bar, our sample mean. But how do we know if X bar is one that we would expect to get, just a sample mean that would normally naturally happen in the course of things, or if our sample mean is very unlikely to happen? Well, a hypothesis test is going to allow us to decide if our claim is true or not. We're going to actually get to see the probability of getting a sample that we get if the null hypothesis is really true. And we can use that p-value or that probability to determine whether or not our null hypothesis is indeed something that we should reject. So how do we do a hypothesis test? Let's recap the steps for doing a one sample hypothesis test for means. The first thing we need to do if we're doing a hypothesis test is to check our assumptions. The second, write our hypotheses and don't forget to define your parameter. Lots of people keep forgetting to define the parameter. If you're using a symbol, you have to define what that symbol represents in the context of the problem. So let's say we're looking at a null hypothesis and we're testing whether or not a mean is really 4. Our null hypothesis would be that mu is equal to, or 12, Then our alternative hypothesis could be anything less than, greater than, or simply not equal to 12. But if we're using the null and the alternative hypothesis today for means, we're going to be using the symbol mu, which represents the population mean or the parameter. But please make sure you're defining what the parameter means in the context of the problem. We'll see that when we go through an example. Third, we certainly have to do our calculations. We're going to find our test statistic, typically a t-test statistic. I'll show you how to calculate that today. And we're going to calculate our p-value. Little known fact, that's our probability value, or the probability of getting what we've got if the null is true. Certainly by this point you know how to define a p-value as the probability getting the result we got, or one more extreme if the null is true. But you may or may not realize that a p-value is simply an abbreviation for a probability value. Last but not least, the heart of what we do in stats is explaining what we're getting in the context of the problem. So the fourth step for doing a hypothesis test is going to be writing our statement in context. Let's review what that statement looks like. This is where we make our decision. Since the p-value is less than alpha, I reject the null. That means there is sufficient evidence to suggest the alternative in context. Or if we read it with the green now, since the p-value is greater than alpha, I would fail to reject the null. That means there is not enough evidence to suggest that the alternative is true. All right, we know our 4 steps. The very first thing we've got to do is check our assumptions for our t-hypothesis test, or t-inference. These are the same assumptions we did for a one-sample confidence interval for means. Let's recap what they are. First and foremost, we're going to have a simple random sample from a population, or if we don't have that and we've got an experiment, we have to have randomly assigned treatments to our experimental units. If we're using a t-inference procedure, that's based on the student's t-distribution. In those cases, sigma would be unknown. And of course, we've got to say that we can assume our distribution to be approximately normal. If we're saying that something is approximately normal, we've got to have some evidence or proof of this fact. What kind of evidence do we need? Well, we'd love to be given that the distribution is normal in the stem of the problem, but that doesn't always happen. Remember, if our sample size is large enough, we say sample size of at least 30, we can say the distribution is approximately normal. And then certainly we saw last time that we have the ability to check graphs of our data and take a look at, let's say, a normal probability plot and look at how closely our data follows a normal pattern. Remember, we only have to use one of these methods to check normality, but these are the three assumptions and conditions that we have to check before beginning a hypothesis test. Once we check our assumptions for inference, it's time to do our calculations. The very first thing we have to do is calculate our test statistic. So today what we're looking at is formulas for our one sample t-test for means. Since sigma is unknown, we use a t-test, and remember our formula for a test statistic is our statistic minus our parameter divided by the standard deviation of our statistic. So in this case, for a t-test statistic, this happens to be our statistic from our sample, that's x bar, or our sample mean, minus our parameter, that's mu, or the population mean, divided by the standard deviation of our statistic. Remember that is S, our sample standard deviation, divided by the square root of n. Once we have our test statistic, we can use our calculator to figure out the p-value. If we're dealing with p-values, usually for proportions and very occasionally for means when sigma is known, we tend to do a z-test. From a z-test statistic, we use the normal CDF feature on our calculator to find our p-value. But for means, most of the time, we're going to be doing a t-test statistic because sigma is going to be unknown. So when we are using a t-test statistic, we're going to use a t-distribution, or on our calculator, we're going to use what is known as the t-CDF function. If you use your t-CDF function, your calculator will ask you for three important inputs. The first is the lower bound, the upper bound, and then finally the degrees of freedom. Remember, your degrees of freedom is always your sample size minus 1. So let's take a look at all of this together. Let's draw and shade a curve, calculate our p-value from our t-CDF calculation. Remember, we've assumed an approximately normal distribution here. We're taking a look at a right-tailed test. Our student's t-distribution and our normal distribution are both symmetric unimodal graphs. So if we're looking at a student's t-distribution, it's also centered at a mean of 0. So we're going to take our t-test statistic on our student's t-distribution. A test statistic of 1.6 would put us above 0, or the center of this distribution. We want to know a right-tailed test, so this is this upper tail area. So our p-value is the probability of getting the test statistic we got, this t, or one more extreme. In this case, more extreme would be greater than this value. So on our calculator, we're going to use the t-CDF feature. The lower bound in looking at our graph is 1.6. The upper bound is a large number approaching infinity, and our degrees of freedom is our sample size minus 1. So in this case, 19. Let's go ahead and calculate our p-value. Using our TI Nspire calculator and a normal calculator page, we're going to click on Menu, and we're going to go down to Statistics and pick up the Distributions tab. On the Distributions tab, you'll see your t-CDF. We're going to enter the data when we select t-CDF. In this case, our lower bound is 1.6, our upper bound is an infinitely large number, and our degrees of freedom were 19. Using our calculator, we can see that our p-value, or the probability of getting a test statistic of 1.6 or greater, is 0.063. So we have about a 6.3% chance of getting this outcome, in this case, assuming the null, which we haven't identified here, is true. Let's take a look now at a two-tailed test. In a two-tailed test, again, we're looking at a t-distribution centered at 0. A t-value are a test statistic of 2.3, so that would be above our value of 0. And on a two-tailed test, we're looking at the probability of it being extreme in this area or extreme in this area. So to find our p-value, we simply find one of the tail probabilities and double it. In other words, our p-value is 2 times the probability of getting a test statistic of 2.3 or 1 greater than that. So again, we're going to go back and use our calculator to calculate the p-value. On our calculator, we're going to select Menu and Statistics. We're going to select the Distributions list, and we're going to go to TCDF. Our lower bound in this case was 2.3. Our upper bound was an infinitely large value, so we're going to type in a very large number. And our sample size was 25, so degrees of freedom of 24. Remember, the p-value we get gives us one tail of our test. Since this was a two-tailed test, we're going to take this answer and multiply it by 2 or double it. So we'll see that the probability of getting a test statistic of 2.3 or greater or negative 2.3 or less would be 0.03, or in other words, we have a 3% chance of this probability occurring. All right, we really recapped everything you need to know about a hypothesis test, so let's put it all together and do an example. For this example, we're going to look at the degree of reading power, or the DRP test. You guys probably took this test when you were in the 3rd grade as well. This is a test given to 3rd grade students to test their reading ability. If you look in the pink, we've got 44 3rd grade student scores from a suburban school district. We're going to look at an alpha level of 0.1 or 10%, and we want to test whether or not there is sufficient evidence to suggest that this school district's 3rd grader reading ability is different from the national mean of 34. All right, so we're going to do a complete hypothesis test here. Step 1 is to state our assumptions. Our first assumption we ask ourselves is, do we have a simple random sample? And yes, we were told we have a simple random sample of 3rd graders. Second, we want to know if the distribution is approximately normal or not. Well, in this case, since the sample size is large, we had a sample of 44, and that meets our burden of proof of a sample size of at least 30, we can say the sampling distribution is approximately normally distributed. We'll also take a look in a minute at a graph of this data. Finally, we ask ourselves, do we know sigma? And in this case, no. Sigma is unknown. That means we're going to use t-inference. We're going to perform a one-sample t-test for means. So let's get started. The next thing we need to do is we need to do our hypotheses. We were testing to verify whether the 44 students in 3rd grade in this district scored differently than the national mean of 34. So our null hypothesis, remember, is always no change, nothing going on, status quo, nothing to look at here. So our null hypothesis will be that the mean is 34. Our alternative, we didn't say whether it was greater or less than. We just want to know if these students are scoring different than the national average. And then, of course, we have to define our parameter, where mu is the true mean reading ability of the district's 3rd graders. Next, we need to do our calculations. Since we're doing a t-test, we need to calculate our t-test statistic. Our t-test statistic is going to be our sample mean minus our population mean from our hypothesis test divided by the standard deviation, which is the standard deviation of our sample, divided by the square root of n. We're ready to plug in values to calculate our test statistic, but we need to know the mean of the sample and the standard deviation of the sample to be able to do this. So we've got to input all of that data into our calculator so that we can calculate the mean and standard deviation of this distribution of data for our 3rd graders. So let's take a look at our calculator again. On our calculator, we're going to enter all of the raw data for these 44 students. To do that, we're going to select Menu, and then we're going to go down, we're going to add a page. My bad, I forgot where we were. We're going to go Control Doc to add a page so that we can get to our Data and Statistics spreadsheet. In our Data and Statistics spreadsheet, we're going to enter the data for all 44 students. But remember, the one thing that you have to do first is you have to arrow all the way up to the top, and you have to define a variable to label each of these columns. So take a moment to enter all of the data on your calculator. So we're just going to go through and we're going to enter all of the reading scores for all of the 44 students. So take a moment to do that now. Once you've got the data entered in your calculator, we can do a couple of things. First, let's get into a new column. When we arrow to the right one column, then we can have our calculator actually find the mean and the standard deviation for us. Remember, to do this, we're going to do one variable stats. So we go to Menu, Statistics, and we select Stat Calculations. We're picking the first choice here, which is one variable statistics. All right, so the screen didn't keep up with me here as I did all that, so let me try it again. We're going to go to Menu, we're going to go Statistics, Stat Calculations, and then we're going to select one variable statistics. We're only having our calculator compute from one list, so number of list is 1. And I called all of my data Y, so we're going to go and tell our calculator where our data is stored. Since mine is in Y, I pick the drop-down menu and select Y. I don't have to change any of the other defaults on my calculator. I can use my mouse to get down here and click OK. Now, we entered 44 pieces of information, so our calculator has the the calculations we're looking for, but they're just kind of way up here. So we're going to have to arrow up until we find all of the values from one variable statistics. And so our calculator has found for us the mean. So our sample mean reading score is 35.0909. Our calculator has also done us the favor of finding S and sigma. Remember here, sigma is unknown. Your calculator does not know if this was a sample or a population, but you do. This is a sample of data, so you're using S, your sample standard deviation, 11.1893. Write those down, and we're going to use those to calculate our t-test statistic. While we're here, we can also take a look at what graph we could produce in order to double check our normal probability assumption. So what we can do is we can add another page. We can say Control Doc to add another page, and this time we can select the Data and Statistics page. We select this page, it actually reads the data from the list in spreadsheets. So right now these points are literally just thrown upon the page. If I click at the bottom where it says click to add variable, I will tell the calculator I would like my Y variable graphed, and this is really just a dot plot of my data. It doesn't really tell me if my data is approximately normal or not, but I can change my plot type to determine that. So to change my plot type, we go to Menu, and there's your choice on number 1, Plot Type. So if I highlight or select Plot Type, I'll see Normal Probability Plot as number 4. So if we select Normal Probability Plot, the black line is a normal probability line, and our blue dots let us see how closely we are approximating a normal distribution. So we look like the data is approximately linear, so we can say that we're approximately normally distributed. Certainly we've got a couple of points that vary from this line, but this is close enough for what we're trying to do. So let's go back now and calculate our t-test statistic and our p-value and finish our hypothesis test. All right, so if you recall, our sample mean was 35.0909. We'll go ahead and round that. Our mean from our null hypothesis is our population mean that we're testing of 34. Our standard deviation for our sample was 11.189, and this is a sampling distribution of all the sample means, so we're dividing that by the square root of our sample size, which is 44 of these third graders. When we calculate this, we get a test statistic of 0.6467. So we're really saying we've got a student's t-distribution here centered at 0. We would like to know the probability of getting this test statistic, 0.6467 or 1 greater. Remember, the probability, the p-value is the probability of getting this test statistic or one that's greater. But we're actually dealing with a two-tailed test here. So we're testing the probability of getting that test statistic or 1 greater, or this test statistic or 1 smaller. So the p-value is literally double that probability. So we're going to calculate the probability of getting a p-value greater than 0.6467 or double that. When we calculate this, we get a p-value of 0.5212. In other words, we have a 52% chance of getting the result we got, even if there was no difference between our students and the true national mean. So guess what? We're definitely going to fail to reject this hypothesis. Let's go ahead and state our conclusion. Remember, we always compare our p-value to alpha, our level of significance, when we're making our decision. In this case, our p-value is much greater than alpha, so we will fail to reject the null hypothesis. That's what we do in terms of the null hypothesis. We also write our conclusion in terms of the alternative. Therefore, we would say, there is not sufficient evidence to suggest that the true mean reading ability of the district's third graders is different than that of the national mean of 34. Every time we make a decision, every time when we do a hypothesis test, we could either get it right or we could make an error. In this case, what type of error is it possible that we have made? We're going to determine the type of error we could have potentially made and state it in context. Remember, we failed to reject the null hypothesis. So the only type of error we could have made here is a type 2 error. We could have decided that the true mean reading ability is not different from the national average when it really is different than the national average. Maybe one of the consequences of that error is that we could have given our students different types of teaching or learning that they could have done so that they could have done better on the DRP reading test, or maybe our kids are accelerated and we really didn't identify that. The error, though, we could have made is we decided that the true mean reading ability is not different when it really could have been. All right, now let's go back and do a confidence interval that associates with this hypothesis test. So in order to do a confidence interval that's going to allow us to test the same thing we did with a t-test for inference, we have to figure out what confidence level that we would use so the results will match the hypothesis test we just did. Remember, our alpha level happened to be 0.1, but we were doing a two-tailed test. That means our level of significance, or our alpha level, was the combination of these two tail areas combined. So if we divide 0.1 in half, we get 0.05 on this end and 0.05 over here. So we've accounted for a total alpha of 10%, which leaves us 90% to be our confidence level. We need to be 90% confident that we know the true the true mean is between blank and blank. So let's go and compute this interval. We're going to use our calculator for this one. All right, let's add a page and go to a normal calculator screen. From our calculator screen, we're going to select Menu. This is Statistics. And we're going to go down and find Confidence Interval. Now, you've got a lot of choices here, so let's be careful. Remember, we're dealing with a one sample interval, and today we're looking at a t-interval for means. So we're going to pick here number 2, t-interval. When we click on that, we can either ask the calculator to read the data that we've already entered, or we can enter our mean and our standard deviations ourselves. Now, since the data is already in my calculator, we can select data here and pick OK. The calculator is going to ask us what list our data is in. Mine was called variable Y, so I'm going to pick Y. Frequency list is going to be 1. And then, of course, we said we were going to be 90% confident. So our confidence level is 90%. And we can use our mouse to click OK. And there is our confidence level. Our confidence interval, Our lower bound is 32.25. And our upper bound is 37.92. We could also do this same thing if we entered the mean and the standard deviation directly. If you see the X bar is given and the degrees of freedom are given and your standard deviation for your sample is given as well. While we're on our calculator, let's recap how to find a hypothesis test on our calculator as well. So kind of from the same thing here, we're going to go Menu, Statistics. Again, that's the class we're in. We use that one a lot. And we're going to go back to the bottom here and pick Stat Test. We are doing a stat test today for a t-test. So you've got all these other choices. Notice these say prop. These are proportions. We're dealing with means. We're going to pick a t-test. This is a one sample t-test for means. And again, we can ask our calculator to read the data that's already there. We're going to click OK. Our null hypothesis is that the true mean was 34. My data is located in the Y list, so I'm going to select the Y list. And our hypothesis, our alternative, was that the mean is not equal to our null, and so we're going to click OK. There's our p-value of 0.52 or 52% that we already found. Our t-test statistic is given, 0.6467, which we already calculated. And there's the sample mean and standard deviation again. You also have the choice here. You could have gone through on your calculator, and when your calculator asked you data or not, let me go back up here to, oh gosh. So I'm going to go menu, statistics, stat test, and then we're going to pick a t-test at the top. Instead of picking data, we could have also picked stats. And so our calculator will simply ask us for our null hypothesis, our mean, and we could enter these values directly because we calculated those earlier on our list and spreadsheets. 189, the sample size was 44, and you're going to be able to get the same values calculating it this way as you would if you had gone through and done the data on your calculator. All right, let's take a look at this confidence interval and what it means, and then we'll be done for today. So we just found our confidence interval to be between 32.255 and 37.927. So that means we are 90% confident the true mean reading level for our third graders is between a reading level of 32.255 and 37.927. All right, so what does that mean? I mean, we've been able to calculate with a confidence interval a prediction. That's what we're really doing here, is predicting the true answer. And we've predicted it's between 32.3 and 37.9. But what does that mean in terms of a confidence interval, a hypothesis test? If you'll remember, the null hypothesis was the true mean is equal to 34. This value is located within our confidence interval. That means because mean is the null hypothesis, the mean of 34 is in our interval, we have no evidence to reject the null. So since the mean value of 34 is in the 90% confidence interval, we do not have sufficient evidence to reject the null. So we fail to reject. All right, that's the end of what we're going to look at today in this video. But if you're a little bit murky or you're not entirely sure you know how to do all of the steps for a hypothesis test, please watch the next video I have posted. In the next video, I'll go through 2 more examples, and we'll do nothing but 2 examples of hypothesis test for one sample means. Thanks for watching. Let me know if you have any questions.